Okay, so you're listening to The Deep Dive, and today we're going to be, well, diving deep, as we always do, into the world of zero-knowledge proofs. And specifically, um, you know how sometimes you want to prove something without actually revealing, all your private information,
Right.
like proving you're old enough to buy something without showing your whole ID. That's the basic idea behind zero-knowledge proofs, right?
Exactly, yeah. It's all about convincing someone something is true without giving away the underlying data.
Now, I know you, our listeners, you're already familiar with kind of the general idea of ZIC. So today we want to focus on the differences between the main players in this space. And we're talking about the non-interactive kinds of ZIC proofs, the NIZKPs. So things like zk-SNARKs, zk-STARKs, and Bulletproofs. We've got some really cool research here covering their math, the security considerations, and even a performance benchmark based on, like a real-world privacy-focused example.
Yeah, the benchmark is really interesting. It gives a good feel for the practical trade-offs you have to make when choosing a protocol.
Exactly. And that's what we're aiming for today, to help you, the listener, understand where these protocols differ in terms of performance and security so you can see which one might be the right tool for your needs.
Right. We'll be looking at the underlying math and cryptography, to see what makes them tick.
So let's start with zk-SNARKs.
Yeah.
What are the fundamental mathematical ideas that underpin these things?
Okay, so with zk-SNARKs, a lot of it boils down to polynomials.
Polynomials. Those are like equations that create curves on a graph, right?
Yeah, exactly. Like x squared plus 2x plus 1, something like that. And the key thing is, if you know the polynomials equation, you can easily figure out its value at any specific point.
Right. So it's like having a secret answer key, but you only reveal the answer to a specific question, not the whole key.
Exactly. That's a great way to think about it. And this idea that you can check a specific point without knowing the entire polynomial is what makes ZC-SNARKs work.
Interesting. And then there's also something about elliptic curve cryptography, right? That always sounds a bit mysterious to me.
Yeah, it sounds intimidating, but it's basically just a different way of doing cryptography, a different set of tools. Imagine, like, instead of working with numbers on a straight line, you're doing math on these special curves.
Curves. So like not just simple addition and multiplication.
Right. We have special operations for adding points on the curve, doubling them, or multiplying them by a number. And crucially, these operations happen within a defined mathematical space, a field.
A field.
Yeah, think of it as a set of numbers where these operations are well defined. And the results, thanks to modular arithmetic, always stay within this field. It's like numbers wrapping around on a clock face.
Okay, so we're doing cryptography on these curves, keeping everything within a certain boundary. But how does this connect to like proving a computation is correct?
That's where the real magic comes in with what's called a quadratic arithmetic program, or QAP.
QAP, got it. And what does this QAP do exactly?
Okay, so imagine you have a computation you want to prove, right? It could be anything, like adding two numbers or something more complex. The QAP takes that computation and transforms it into a special form using polynomials.
So we're going from like regular math to this polynomial world.
Exactly. And there are a couple of steps involved. First, you turn the computation into something called an arithmetic circuit. Then that circuit gets transformed into a rank 1 constraint system, or R1CS. And finally, that R1CS becomes the QAP, which is basically a set of polynomial equations that represent your original computation.
Okay, lots of steps. But the end result is that my original computation, whatever it was, is now expressed using these polynomials. And then how do these polynomials help prove something?
All right, imagine you have a target polynomial called t, which represents your entire computation. For a zk-SNARK proof to be valid, this t must be perfectly divisible by another polynomial, z, without any remainder. If it divides cleanly, it means all the conditions in the computation have been met. Mathematically, we can say t equals some other polynomial h multiplied by z.
Okay, I think I'm following. So the prover, the person trying to prove something, they create this t based on their secret input. And the verifier, who's checking the proof, they need to see if t is divisible by z without actually seeing the secret input, right?
Precisely. And that's where all the clever cryptography comes in, using these polynomial commitments and elliptic curve operations we talked about. But one thing that's really important and actually quite unique to zk-SNARKs is this idea of a trusted setup. You're familiar with that, right?
Yeah, the trusted setup. It's where some initial secret information, sometimes called toxic waste, is generated to create a common reference string, or CRS. And both the prover and verifier use this CRS for the proof.
Exactly. The key point here is that this toxic waste used to make the CRS must be destroyed after the setup. If someone got hold of it, they could potentially create fake proofs that would have looked completely legitimate.
Oh, wow. So there's a lot of trust involved in setting up a zk-SNARK system.
Yeah, that's the trade-off. You get these really small, efficient proofs, but you're relying on this initial ceremony being done correctly and securely. And that's a fundamental consideration with zk-SNARKs.
That sounds like a pretty big vulnerability. How do they try to reduce that risk in practice?
One common approach is to use something called multi-party computation, or MPC. Instead of a single entity generating the toxic waste, multiple parties participate in the setup. The idea is that as long as at least one of them is honest and destroys their share of the secret, the system remains secure. It's like having a secret that's split into pieces and you need all the pieces to reconstruct it.
So it's kind of like a group secret. And if even one person keeps their piece secret, the whole secret is safe. But if everyone decides to work together, well, then the system breaks down.
Exactly. So MPC is a way to try to distribute the trust, making it harder for a single malicious actor to compromise the system. But it's not a foolproof solution. If all the participants collude, the security is gone.
So it still feels a bit fragile, doesn't it? Relying on at least one person being honest.
Yeah, that's a valid point, and it emphasizes that the whole setup process needs to be incredibly carefully designed to minimize risks. There was even that real-world case with Zcash where I think it was transcripts from their MPC setup accidentally leaked some of the toxic waste information. So even the way you do the setup matters a lot.
Wow, okay. And then there's also the requirement that the CRS, that common reference string, needs to be disclosure-free,
Yeah.
right?
Okay.
What does that mean and why is it so important?
Right, good point. If the CRS itself revealed too much information about the toxic waste that was used to create it, then an attacker might be able to figure out enough to create those fake proofs. So it's another layer of security that needs to be carefully considered.
Okay, so a lot of delicate points with the setup.
Yeah.
But even beyond the trusted setup, there are other security concerns with zk-SNARKs, right?
Yeah, definitely.
Like I remember reading that they rely on certain cryptographic assumptions that might be vulnerable to quantum computers.
Right. Specifically, they use elliptic curve cryptography and rely on the hardness of the discrete logarithm problem.
So if someone builds a powerful enough quantum computer, could they crack the code and create fake proofs?
That's the worry. Shor's algorithm, which is a quantum algorithm, could potentially solve these problems much faster than classical computers.
So zk-SNARKs might not be future-proof against quantum attacks. That's something to keep in mind.
Definitely a long-term consideration.
And then beyond the kind of fundamental cryptography, there's also the risk of messing up when actually building the proof circuit itself, right?
Oh, absolutely. Like if you don't handle input values properly, you could get overflows or underflows, which can lead to vulnerabilities. The Aztec network had a vulnerability a while back where they missed a check on the length of a data index. This allowed attackers to spend the same note multiple times because the system didn't properly restrict the input parameters.
So even if the underlying math is solid, a bug in the implementation can still create a security hole.
Exactly. It highlights the need for careful design and rigorous testing.
Okay, so we've talked about the math and security considerations. What about performance? How do zk-SNARKs stack up in practice?
Well, that's where the benchmark comes in. And as you mentioned earlier, this specific benchmark was focused on a privacy-preserving scenario.
Right, a kind of real-world use case.
Yeah.
And the results showed that zk-SNARK protocols, specifically the ones using the Rust-Bellman and GoNARK libraries, generally produced the smallest proof sizes.
Small proof sizes are a big advantage, especially in situations with limited bandwidth or storage, right?
Exactly. And what's interesting is that these sizes didn't change much even when they increased the complexity of the computation in the benchmark.
So very consistent proof sizes. How about the time it takes to create and verify these proofs?
For proof generation times, zk-SNARKs were comparable to zk-STARKs. But when it came to verification times, they were a bit slower than z-STARKs, although still faster than Bulletproofs in this particular test.
So a bit of a trade-off there. Smaller proofs, relatively fast generation, but verification can lag behind.
Yeah, and of course we can't forget that trusted setup requirement. So taking everything into account, where do you think zk-SNARKs would be a good fit?
Well, if you need really small proofs, and you're okay with the trusted setup process, zk-SNARKs are a strong contender. And the research actually suggests they could be particularly well suited for like Internet of Things applications where devices often have limited storage, bandwidth, and processing power.
Yeah, makes sense. The small proofs would be a huge advantage there.
Ah, okay.
Okay, so that's zk-SNARKs. Now let's shift gears and talk about zk-SNARKs. What are the key differences we see here compared to zk-SNARKs, especially in terms of their mathematical foundations?
All right, so one of the big shifts with zk-SNARKs is the heavy reliance on cryptographic hash functions.
Hash functions, like SHA-256 or things like that.
Exactly. Things like SHA-3, where you feed in data and it spits out a unique fixed size output, essentially like a fingerprint of the data.
Why are hash functions so important for zk-SNARKs?
Well, they provide a few crucial things. First, data integrity. You can use a hash to ensure that data hasn't been tampered with. Second, they act as a good source of randomness, which is essential for many cryptographic protocols. And third, you can use them to create binding commitment.
Binding commitments.
Yeah, like saying, I'm committing to this value, but without actually revealing the value itself. You can achieve this by hashing the value, and then later you can reveal the value and show that its hash matches the commitment.
Ah, interesting. So hash functions are like a Swiss Army knife for cryptography.
Exactly. And then another crucial element for zk-SNARKs is the use of Merkle trees.
Merkle trees, I've heard of those. They're like a way to create a digital summary of a large amount of data, right?
Exactly. You split the data into chunks, hash each chunk, then hash pairs of those hashes, and you keep going up the tree until you reach a single root hash.
And that root hash acts like a unique fingerprint for the entire data set.
You got it. And the cool thing is, if you want to prove that a specific piece of data was part of that original set, you only need to provide that piece of data and a small authentication path of hashes leading up to the root. The verifier can then recalculate the hashes along the path and see if they match the root hash.
Oh, I see. So it's like proving a specific page exists in a book without having to show the whole book. Just show the page and a few key sentences that connect it back to the table of contents.
Perfect analogy. And then, on top of hash functions and Merkle trees, zk-SNARKs also use this algorithm called the fast Fourier transform, or FFT.
FFT, isn't that something used in signal processing?
Yeah, the same algorithm is used in a bunch of different fields. In the context of zk-SNARKs, the FFT is used to efficiently switch between two ways of representing a polynomial, by its coefficients, which are the numbers in front of the variables, and by its values at specific points.
So it's like translating between two different languages that describe the same polynomial.
Exactly. And the FFT does this translation incredibly fast, reducing the number of calculations needed from something like on squared to on log n.
Okay, so it's a big speed boost.
Yeah.
And why is the speed so important for zk-SNARKs?
Because Stark proofs involve a lot of polynomial manipulation, and doing those calculations quickly is essential for making the whole system practical.
Makes sense. And I remember reading something about roots of unity being involved in the FFT as well.
Ah, yes. Roots of unity are these special numbers that, when you multiply them by themselves a certain number of times, you get back to 1. They have these nice symmetrical properties that the FFT algorithm exploits to achieve its efficiency.
So it's like a mathematical trick that makes the FFT super fast.
Pretty much. And then, to add another layer of complexity, zk-SNARKs also use Reed-Solomon error-correcting codes.
Error-correcting codes. Those are like adding extra information to data so that even if some of it gets lost or corrupted, you can still recover the original.
Exactly. It's like adding redundancy to make the data more robust. In zk-SNARKs, they apply these codes to the polynomial that represents the computation, making it longer and more resilient to errors.
So it's like adding a safety net to the whole process. And finally, there's this concept of polynomial commitment schemes. What are those all about?
So a polynomial commitment scheme allows a prover to commit to a specific polynomial without revealing the actual polynomial itself. And later, the verifier can ask for evaluations of that polynomial at specific points and check that they're correct, still without learning the full polynomial.
So it's another way to keep things hidden while still allowing for verification.
Exactly. It's a key part of how zk-SNARKs work. And they use a specific method for this called the Fast Reed-Solomon Interactive Oracle Proofs of Proximity, or FRI for short.
FRI. Bit easier to say than the full name. Okay, so lots of complex math going on in zk-SNARKs. But one huge difference compared to zk-SNARKs is that they don't require a trusted setup, right?
Exactly. That's one of the big advantages of zk-SNARKs. No need for that initial ceremony and the potential risks associated with it.
So that's a big point in their favor. No toxic waste to worry about.
Right. They achieve this by using different cryptographic primitives and constructions that don't rely on those initial secret parameters. So with Starks, you're trading off smaller proof sizes for the benefit of no trusted setup and quantum resistance.
And speaking of quantum resistance, that's another major plus for zk-SNARKs, right?
Exactly. Unlike zk-SNARKs, which rely on elliptic curve cryptography that could be broken by powerful quantum computers, zk-SNARKs use cryptographic hash functions, which are thought to be quantum resistant.
So they're more future-proof in that regard.
That's the thinking, yeah. Although, of course, the future of cryptography is always uncertain.
True. But at least they're built on primitives that are considered safer in a post-quantum world.
Exactly. Now, there was one interesting security point that the research brought up regarding the Winterfell library, which is a specific implementation of zk-SNARKs used in the benchmark. Do you remember what that was?
Oh, right. It seems that Winterfell, at least in its current version, doesn't fully implement perfect zero knowledge.
Yeah, that's a key point. It's primarily focused on proving the correctness of computations, which means there's a potential for some private information to leak out in the proof itself. Unlike zk-SNARKs and Bulletproofs, which are designed from the ground up to prevent any information leakage.
So that's something to be aware of when using Winterfell. It might not be suitable for applications where privacy is absolutely paramount.
Exactly. You need to choose the right tool for the job.
Okay, so no trusted setup, quantum resistant, but potentially some limitations with perfect zero knowledge in certain implementations. How did zk-SNARKs perform in terms of the actual benchmark?
All right, so the benchmark results showed that zk-SNARKs, while having comparable proof generation times to zk-SNARKs, and sometimes even being faster, produced the largest proof sizes by far.
So that's a big trade-off.
Yeah, the no trusted setup in quantum resistance comes at the cost of larger proofs. And what's more, these proof sizes grew as the complexity of the computation in the benchmark increased.
So the more complex the computation, the bigger the proof. What about verification times?
That's where zk-SNARKs really shined. They had significantly faster proof verification times compared to both zk-SNARKs and Bulletproofs in this particular benchmark.
So even though the proofs are larger, they can be checked much faster.
Exactly. That fast verification could be a huge advantage in certain applications.
Given all these characteristics, where do you see zk-SNARKs fitting in best?
While the large proof sizes suggest they're probably not the best choice for applications with very tight constraints on bandwidth or storage, but they could be ideal for things like cloud computing, data centers, or machine learning where you have a lot of storage and network capacity.
Right, those environments wouldn't be as bothered by the larger proofs.
Exactly. And they're also really good for what's called verifiable computing.
Verifiable computing.
Yeah, it's basically proving that a computation was performed correctly without having to rerun the whole computation yourself. And zk-SNARKs are great for this because they can produce a succinct proof that someone can quickly verify.
Okay, so they're like a proof of work done, in a way.
In a sense, yeah. So for those types of applications, zk-SNARKs could be a really powerful tool.
Awesome. Okay, so that's zk-SNARKs. Finally, let's move on to Bulletproofs. What can you tell us about the mathematical ideas behind them?
So the research we have doesn't go into a ton of technical depth on the specific math behind Bulletproofs, but it does mention that they have their own distinct mathematical foundations.
Okay, so they're not just a variation on SNARKs or STARKs. They have their own thing going on.
Right. The research we have focuses more on their properties and how they perform compared to the other protocols.
Got it. So what about the trusted setup and quantum resistance for Bulletproofs? Where do they stand on those?
Similar to zk-SNARKs, Bulletproofs do not require a trusted setup.
That's a big plus, right?
Yeah, no toxic waste or complex ceremonies to worry about. But on the downside, they rely on cryptographic primitives that are not considered to be quantum resistant.
Ah, so they're in the same boat as zk-SNARKs in that regard. Potentially vulnerable to future quantum computers.
Exactly.
And what about their overall security goals? What are they designed to prevent?
Like zk-SNARKs, Bulletproofs are designed to achieve zero knowledge. That is, they prevent the verifier from learning anything about the secret information beyond the fact that the statement being proven is true.
So they share that core privacy goal with SNARKs, but without the need for a trusted setup.
Precisely.
Okay, interesting. Now, how do they do in the benchmark? How do they compare to SNARKs and STARKs in terms of performance?
All right, so in terms of proof sizes, Bulletproofs fell somewhere between z-SNARKs and zk-SNARKs. They were larger than SNARK proofs, but smaller than STARK proofs.
Kind of a middle ground then.
Yeah, and like zk-SNARKs, their proof sizes also increased as the complexity of the computation went up in the benchmark.
So more complex computation, bigger proofs. That seems to be a common trend.
Yeah, it makes sense. The more you need to prove, the more information needs to be included in the proof.
Okay, how about the time it takes to generate and verify these proofs?
That's where bulletproofs seem to lag behind a bit in the benchmark. They had noticeably slower proof generation and verification times compared to both zk-SNARKs and zk-SNARKs. And this performance seemed to degrade even further as the computations got more complex.
So slower overall, and the gap widens with more complex computations. That's a significant disadvantage.
Yeah, definitely something to consider. But the research does point out that bulletproofs have some unique capabilities that weren't fully utilized in this particular benchmark.
Oh, right, like,
Well, one thing is batch verification, where you can verify multiple proofs at once much more efficiently than checking them individually. This can be a big win in applications where you have a lot of proofs to verify.
so it's like getting a bulk discount on verification.
Exactly. And the cool thing is that this batch verification can even work for proofs related to different computations as long as they use the same public parameters.
Oh, that's interesting. So you can bundle together proofs for different things and verify them all at once.
Exactly. And then there's also this concept of proof aggregation.
Proof aggregation, what's that?
It's basically taking multiple proofs and combining them into a single, smaller proof.
Hmm.
This can be really useful for reducing the overall size when you have several things to prove.
Ah, I see. So it's like compressing multiple files into a single zip file.
Yeah, a good analogy. And one more thing to keep in mind is that while the benchmark focused on general computation proofs, bullet proofs are actually especially good at something called range proofs.
Range proofs, what are those all about?
Range proofs are specifically designed to prove that a value falls within a certain predefined range without revealing the exact value itself.
So like proving you're over 18 without revealing your exact age.
Exactly. Or proving that your income is above a certain threshold for a loan without disclosing your exact salary.
Oh, I see. That's really useful for privacy-sensitive applications. So despite the slower performance in the general benchmark, bulletproofs have these specialized capabilities that could make them really attractive for certain use cases.
Exactly.
So overall, where do you see bulletproofs fitting into the landscape?
Well, the lack of a trusted setup makes them a strong alternative to zk-SNARKs when that's a deal breaker.
Yeah.
And their strength in range proofs makes them perfect for applications like financial transactions, income verification, age checks, things like that. And with their efficient batch verification, they could be a good fit for blockchains where you need to verify lots of transactions. In fact, they're already being used in projects like Monero.
Okay, so they have their niche, even if they're not the fastest overall.
Exactly.
All right, so we've covered a lot of ground here. We've looked at the math, the security, and the performance of zk-SNARKs, z-STARKs, and bulletproofs. What are the key takeaways when we compare them head-to-head based on this research?
I think the benchmark really highlights the core trade-offs you have to consider. zk-SNARKs give you the smallest proofs but come with the complexity and potential risk of a trusted setup. zk-SNARKs provide fast verification and quantum resistance, but produce much larger proofs. And bulletproofs offer a middle ground in terms of proof size, don't require trusted setup, but are generally slower, although they excel at range proofs and batch verification.
It really drives home the point that there's no one-size-fits-all solution, right? The best protocol totally depends on your specific needs.
Absolutely. You have to think carefully about whether a trusted setup is acceptable, how much proof size matters versus verification speed, and whether you need to worry about quantum computers in the future.
Right. And it's fascinating that even when different libraries implement the same underlying protocol, like that Groth16 zk-SNARK in Rust and Go, you can see noticeable differences in performance, especially in things like the key sizes.
Yeah, implementation details matter.
So what would be your advice to someone who's trying to choose the right zero-knowledge proof protocol for their project? Where should they start?
Honestly, I think the best approach is to start by building some proof of concept implementations. Try out a few different libraries and protocols that seem relevant to your use case and see how they perform in practice. Experiment with different settings, especially for something like zk-SNARKs, to see how you can optimize for your needs. And don't be afraid to explore hybrid approaches that might combine the strengths of different protocols.
Yeah, that makes sense. Get your hands dirty and experiment. And hopefully this deep dive has given our listeners a solid foundation of knowledge to help them make those decisions and, maybe save them some time and effort in the process.
Exactly. And looking ahead, I think it's really interesting to consider how the evolving field of cryptography, especially the threat of quantum computing, will continue to shape these different zero-knowledge proof technologies, will we see more focus on those quantum-resistant SNARKs? Will researchers find ways to make SNARKs quantum secure without sacrificing their efficiency? It's a dynamic and fascinating area to keep an eye on.
Yeah, lots of exciting developments on the horizon. Well, thank you so much for joining me on this deep dive into zk-SNARKs, zk-SNARKs, and bulletproofs. It's been a really enlightening discussion.
My pleasure. It's always great to unpack these complex topics and explore the possibilities.
And to our listeners, we hope this deep dive has given you a clear understanding of the zero-knowledge proof landscape. We encourage you to dig deeper into the research we've talked about, maybe play around with some of those libraries, and if you have any questions or thoughts, feel free to reach out. Until next time, keep exploring the fascinating world of cryptography.